Hey math kids, today we're going to talk about average rate of change, and if you haven't seen the slope review video, I would watch that first just to make sure you're good on slope. But these are three equivalent statements for slope. We have the change in y over the change in x, or delta y over delta x, which translates into y2 minus y1 over x2 minus x1, and we can also envision that as rise over run. Now the only difference between slope and average rate of change is that slope is defined only for a linear function or a line, and that's because the slope or the average rate of change on that line is the same everywhere. So if we go rise over run right here, it's going to be the same as the rise over run right here. Now if we have a function like a parabola or an exponential function, we can see that the slope changes. And so if I were to pick 2 points here and here and then draw a line, that slope is going to be different than if I draw points here and here and connect that line. So that's why we call this average rate of change for a couple reasons. It's the average because when we pick these 2 points and draw a line, it's not exactly how the curve is, but it's pretty close, and in a lot of applications it's good enough. Same with this exponential function. If I go from here to here, that's a pretty shallow slope, but if I go from here to here, that's a really steep slope. So once again, we're going to refer to that as average rate of change because it is a rate of change, but we're just averaging out the points in between those 2 points that we choose. Okay, now I'm just going to show you how we approach this on a graph. Now, this is the equation of this graph. So unless on an assignment it says not to graph it, or it says to do it by hand or use the equation or something, if it says that, you can't use this method. But if you're allowed to, you can graph an equation. So I've done that on Desmos. I just took a screenshot, and it will give you a interval, which is just the x values that it wants you to look at. So I'm going to look at it in between -2 and -1. So what that means is it wants me to look at it from here to here. We don't care about anything else that's going on the function. So I'm going to put dots on the function at those 2 x values, and then I'm going to pretend like this is just a line. So I'm just going to connect those dots, okay, and I'm just going to find the slope. Now we have to go down 1, 2, 3, 4, and then over 1, 2, 3, 4, 5. Now that's not really, that's just with squares, right? So what we're doing, we go down, let's see, these are 1, 2, 3, 4, 0.2, 0.4, 0.6, 0.8, 1, okay. So each of those we're dropping 0.2. So we're going to go 1, 2, 3, 4. So from here to here, we had to drop 0.8. So that's our rise, or the top when we're thinking rise over run. So we get -0.8 divided by, and then we run 1. Because from -2 to +1 right here, we're going to go 1. And so if we go -0.8 divided by 1, that's just going to be -0.8. And that's our slope, or our average rate of change, just on that section. Okay. Now, what if we treated these squares? Let's see how I did that originally. So we just went 1, 2, 3, 4. So that'd be -4 over 1, 2, 3, 4, 5. So if we did -4 over, +5, is that the same thing as 0.8? And the answer is yes. So if you want to treat just those boxes as whole values, you'll actually end up getting the same answer. And it might be easier to think of it that way, but it's up to you. Okay? Alright, let's move on to the next section on this one. So this time we're going to look at the interval from -1 to 0. So we're at -1, we're at 0. Once again, we put a dot at -1, dot at 0, staying on there, and we're going to find the rise over run from here to here. So we drop down 1, so that's a -1. We run 1, 2, 3, 4, 5, and that's 5, -1/5. Now, each of these is 0.2, so I drop down -0.2, run 1, so that's -0.2, which is the same thing as -1/5. So once again, either way you do it is fine. Now I'm just going to do one more to show you a positive slope. Now if I go from this point to this point, it's, I guess I didn't realize that right there. It wasn't exactly on that square, but we can kind of pretend like it is. So we're going to go up 1 over 5 squares, and so our slope is 1/5, which in this case we call our average rate of change. So that was for the interval from 0 to +1. And we could continue and do 1 to 2, 2 to 3, whatever, whatever you want. But that's essentially how you do it. Now let's look at an exponential function and do the same thing. Okay, so I'm going to look at -1 to 0. So I go to the function, -1, 0. Okay, this is a little tricky because right here we're about halfway. And so our rise from here to here is going to be 1 square, 2 square, 2.5 squares. And it's positive, it's going up this time. And so it's 2.5. And then we run 5 squares. So 2.5 divided by 5. Let's just do that on a calculator. So we say 2.5 divided by 5. That gives us 0.5. So our slope is 0.5, or if you want to write it as 1/2. Once again, that's our average rate of change. It's telling us the slope of the line that's in between those 2 points. Now this is going to curve, so it's not exactly that, but if we averaged out all those slopes at every single point, this is what we would get. So that's 1/2. Now let's try one more. Let's go from 0. Let's go to 0 to 2 actually. Let's just do this big jump. So 0's there, 2's all the way up there. And so this one worked out nice though, because we can do the big squares, or we can do all the little squares. But once again, it doesn't matter. So if we do it thinking of the big squares, we write 1, 2, 3, and we run 2, so it's 3/2. Now if we do all the little squares, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Over 5, 6, 7, 8, 9, 10. And if we simplify that, that becomes 3/2. So once again, it doesn't matter if we use the big squares or the little squares, we will end up with the same average rate of change. If you need additional help, please come to Math Lab. Until then, calculator.